Okay, great. Um, I okay, great. Welcome everyone. Thank you for joining us today at our seminar. We have a very exciting program today. We have a three-part series. I'm presenting the first part on study design of biomedical research studies. And then Jie Chen is going to present some introductory statistical methods with some practical examples in SAS and R. And then Dan Gunnarsson is going to be presenting structural equations modeling in his part of the talk. So my name is Clement Ma. I'm a statistician at the Dana-Farber Cancer Institute and also Boston Children's Hospital. And I'm very pleased to present here today. I'm going to be talking about some design principles for biomedical research studies. So to start, there's a wide range of different preclinical and clinical research studies in oncology today. And really each type of study has their own, have their own specific design requirements. And just thinking through this talk, I wanted to give a more broad overview of some general design and statistical principles for biomedical research studies. So study design is really the specific plan or protocol for conducting a research study. And it's very important to have a well-written, well-thought-out study design because poorly designed studies may end up, you may not be able to answer the scientific questions that you're trying to address in your study. A poorly designed study can also introduce bias in the results and may lead to false positive results. And I think the key part is that while you can change the statistical analysis kind of after the data have been collected, changing the analysis won't really rescue a poorly designed study. So this is something that, as an investigator, you want to make sure you think about right from the beginning. So in general, I would say there would be 5 steps that you want to consider when trying to design a study. First, you want to think about your study objectives and your endpoints, the measurements that you're going to be making. We want to be careful in defining our study population. And then we're going to basically select the experimental design, and there's different pieces that you may want to consider in your particular study. And then next, you would want to calculate an appropriate sample size for your study so that you'll have enough information, enough power to answer the question that you're trying to address. And then finally, writing out the statistical methods in a very clear analytic plan is also very important. So let's start with the first piece, defining the study objectives. So these objectives really pose the scientific questions to be addressed in your study. And in general, a study should have one primary objective and a number of secondary and exploratory objectives. You would want the objectives to be clear, concise, specific, and most importantly, quantifiable, something that you could measure objectively. When you're trying to write the objectives, you may consider some keywords to determine, to estimate, evaluate, describe, identify, or compare. And there are other words you may want to use. But generally, a study aim or objective would begin with a statement to determine X, to estimate something. And if you think more broadly, we can kind of split objectives into 2 general classes, descriptive objectives and comparative objectives. So for descriptive objectives, our goal here is to estimate a parameter of interest in the study population. So it might be trying to estimate the survival rate of your population or whether your treatment has a good response rate. We also want to estimate a measure of precision that is associated with this estimate. So like a standard deviation, range, 95% confidence interval, for example. For descriptive objectives, generally there will be no formal hypothesis or statistical testing. You're not going to run a comparison. It's just really describing your data using an estimate. So some examples, to identify the number of copy number variants in a certain population, in a certain gene, to describe the overall survival of patients diagnosed with a certain disease, to assess the feasibility of conducting a survey in patients with X. Now, in comparison, for comparative objectives, the goal here is to compare a certain outcome or endpoint between groups, or compare the outcome that you measure in your study versus some historical control or some threshold. In this case, you would want to perform some type of statistical test and then calculate a measure of statistical significance. It could be a p-value, q-value, posterior probability. So some examples, to identify the genetic variants associated with disease X, or to determine if the treatment response is higher in patients treated with drug A versus drug B. So I wanted to give some examples of objectives and kind of examples that we want to make some improvements on, give some commentary, and then maybe suggest an alternative objective. So in the first case, on the left, there's an objective to determine if the drug improves patient outcomes. So, the question would be, what are these outcomes that we're trying to improve? And how are we going to quantify this improvement? So is it simply yes or no, the patient improved or not based on a threshold? Or are we looking at a continuous measure of outcome? They have 20% better survival at 5 years, or they have 10 points higher on their quality of life score. So, an improvement to this objective could be to determine if patients in treatment arm A have a higher event-free survival than those in treatment arm B. So, event-free survival is that outcome that we're going to be comparing between the treatment arms. So here's another example, to characterize changes in patient quality of life after treatment. So the question would be, what time points are we comparing between, and how are we going to quantify the change? Is this an absolute difference in the change, or is it a percentage difference? So an alternative objective would be to characterize the percentage change in the total quality of life score from baseline to 12 weeks after treatment. So this would be an example of a descriptive objective. And then finally, this is something that I see very often when working with investigators, to compare the T cell, B cell, and cytokine profiles at 4 weeks, 12 weeks, 6 months, and 1 year. So basically, there's too many objectives, too many outcomes in a single objective. And when we say compare, we need to specify what the comparison groups are. So the improved objective would be to compare the number of CD4 and CD8 T cells at 4 weeks, 12 weeks, 6 months, and 1 year between wild type and mutant mice. So these are just some examples. I mean, in your own research study, you have to think about what makes sense for your own study. So for the primary objective, this is your main scientific question that you want to address in your study. And generally, the primary objective will determine the study design and sample size. So you're going to design the study around the primary objective. Specifically for comparative objectives, I would generally recommend that you have a single primary objective that compares a single endpoint or outcome between groups. Because if you have additional objectives or outcomes within the primary objective, then you would need to control for multiple comparisons. I'm going to be talking about this a little bit later. Now for secondary and exploratory objectives, these are some additional scientific questions that you want to investigate. But they're different from the primary objective as that they're more for hypothesis generation, for future studies, or simply to collect data so you can design a future study. But it's still important to specify how you're going to measure and evaluate these secondary and exploratory outcomes. You still want to follow the same principles for all objectives. And again, we want to avoid excessive numbers of secondary and exploratory objectives because you might encounter a multiple testing problem. And generally, we would suggest that you still assess power for these secondary or exploratory objectives using the sample size that you've determined from your calculation for the primary objective. So do you have sufficient power to address all these additional objectives given a certain sample size? All right, so next we need to think about the outcomes that you're going to measure, or the endpoints. These are the events or characteristics that can be objectively measured within each study subject. So what we want to define is when the outcome will be measured, how it will be measured, what assay, what survey, what is the method of measurements. It's important to think about the type of outcome that you're going to get. What kind of result will you get after you measure this? Will this be a binary outcome, yes or no, present or absent? Is it ordinal? So these are kind of ordered categories, such as low, medium, high, a continuous outcome, or change over time. So there are many types, but the type of outcome will really determine the type of analysis that you're going to do at the end. So it's good to think about this when you're writing the objectives and the outcomes. And also good to note that what are the units of measure for these outcomes. So I want to again present a couple endpoints as examples. The first one is treatment response rate. Now this is a rate, so it's a proportion. It ranges from 0 to 100% in your study population. So this is something that you measure across the population. It's not something you measure per study subject. And we want to be careful when you say treatment response. How do you determine whether a certain subject has responded or not? So alternative would be something more specific. So treatment response, it's a binary endpoint, as defined as greater than equal to 6 out of 8 weeks with platelet counts greater than this threshold during weeks 5 to 12 of therapy. So it's very clear, if you achieve this, you're a responder to the treatment, and if you fail this definition, you're not a responder. So this is something that you want to be very careful when you define it. Because the worst thing that would happen is you've collected a lot of data, and when you get to analyze it, you can't exactly determine who is responding or not. And you don't want to be changing the definition as you go when you do the analysis. So second, event-free survival, EFS. So again, EFS is a proportion measured for the whole population, not for a single individual or a subject. For any survival outcomes, you need to think about what the starting time point is. Are you measuring from date of diagnosis, from date of surgery, or maybe another time point? And then for the events, which events are included? So an alternative endpoint would be time to date of diagnosis to progression, relapse, or death. So those are events. Or to date of last follow-up if the patient was alive. And then you would go on to define what is a progression and what is a relapse. So it's very clear when you go to analyze it how you can actually calculate it, this event-free survival. So finally, let's say you're interested in patient distress. So the first question is, how are you going to measure distress, and when this distress measurement will be taken? So the improvement or the suggestion would be the total distress score at 3 months as measured by the Memorial Symptom Assessment Scale. So something very specific and something that we can measure very clearly. Okay, so the next step is to think about your study population. Who are you going to include or exclude from your study? And it's very important to set your inclusion and exclusion criteria before the study starts. You don't want to be changing kind of ad hoc as you're going along. So with defining your inclusion and exclusion criteria, generally there's a balance between kind of more broader kind of general inclusion versus a very restricted inclusion set of inclusion criteria. So if you have broad criteria, you're going to be able to accrue your subjects more quickly. Since you're looking at a more broader population, the results are more likely to be generalizable. But you're going to end up with a more heterogeneous population when you go analyze it. So if the treatment was only effective in one subpopulation, having a heterogeneous population may dilute that treatment effect that you're looking for. Whereas if you have a strict set of criteria, you're going to have a harder time recruiting and accruing subjects. Your results may be less generalizable, but you're going to have a more homogeneous population, and you may have better control over confounders and other characteristics. And again, if you're changing your inclusion-exclusion criteria kind of in an ad hoc manner, you're going to introduce selection bias. So the selected study subjects are not really representative of the population that you're trying to analyze. All right, so next I'm going to go into some design considerations that you may consider in your particular study. The first step is, really, are you thinking of a prospective study where you're going to collect data as a study progresses? So on the right, there's a plot. You can see the timeline. Start of the study is up now, and then you're going to conduct the study moving forward into the future. The key is that you're going to be able to measure the baseline exposures and confounders and kind of subject characteristics before the outcome has occurred. So you're going to measure it before this or at the start of the study at baseline, and then your outcomes are measured kind of as you go along. So it might be at one or more time points. So the properties of prospective studies are that this usually has better measurement of exposures and potential confounders, thus reducing bias. You're able to, because you're collecting data as you go forward, you're probably likely to have more uniform and rigorous data collection compared to retrospective studies. The downside is generally prospective studies would be more expensive and maybe more time-consuming to conduct. So in contrast, retrospective studies, all of the data, the exposures and the outcomes have already happened in the past. So you're at the start of the study, you're going to look backwards in time, and you're going to capture a cohort of subjects where you're going to measure their exposures and their outcomes of interest. This is a good design for generating hypotheses or when your patient population or outcome is rare, and it's going to take you a long time to collect many subjects with this certain outcome if you go in a prospective study. They're generally inexpensive and quick to complete. The downside is that the exposures or outcomes of your subjects may be missing or inaccurate. So another consideration you may want to think about is randomization when you are trying to compare a certain intervention or treatment between one or more groups, or two or more groups. So basically, randomization is a method to unpredictably assign the intervention to the study subjects. And the real benefit of randomization is that it's able to balance both known and unknown factors, characteristics of your subjects between the different treatment groups. And this is one way you can reduce the selection bias. And as such, in randomized controlled trials for drug development, this is the kind of the gold standard. This is the most reliable evidence we can have for intervention efficacy in humans. And there have been papers in kind of talking about reproducible research in preclinical studies where they recommend that randomization techniques can also be applied to mice studies, for example. So a successful randomization really requires two things. So we need to be able to generate an unpredictable sequence of intervention allocations, so either treatment A or B. And then we want to be able to conceal this allocation until the intervention, until the assignment of the intervention to the patient. So we don't want to be able to predict which intervention the next individual will get. So there are several types of randomization you may consider. The first one is simple randomization. Basically, you're going to randomize basically only on the allocation ratio. So let's say you want to randomize 1-to-1 to 2 treatment groups, then essentially it's a coin flip, 50-50. So on the right, I've just given a series of randomized allocations for 2 treatments, treatment A and B, to 40 subjects, and generated this random string. And at the end, there were 17 subjects assigned to treatment A and 23 subjects assigned to treatment B. It's somewhat, it's random. You're not going to get exact balance between the treatment groups every time. So the advantage of a simple randomization like this is that it's unpredictable. You're not going to be able to tell what the next treatment intervention would be. And it's really good at reducing selection bias. However, as you can see, that you could end up, if you're unlucky, end up with unbalanced numbers of subjects per group. You could also end up with unbalanced characteristics in the subjects between groups. So you may end up with more males in treatment A than in treatment B. And that's something you may have to control for in your analysis. And then finally, again, because it's a simple coin flip here, you may get long runs of subjects assigned to the same treatment. So you can see here, for these patients, these sequence of patients, there's 7 individuals who got treatment B. So if for some reason you had to end the study early, you're going to have a large imbalance in your treatment allocation. So kind of one solution to this is a blocked randomization. So you're going to randomize within a specific block of patients, a group of patients, where you specify this. So in the example on the right, I've, again, randomized the treatments to 40 subjects, but now we have a block size of 8. So within each row, which is 8 subjects, there's going to be a balanced number of treatment A or B. And then we're going to repeat this kind of with each of the 5 blocks. So the advantage here is that we ensure there's going to be roughly balanced numbers of individuals in each treatment group at any point in the trial. But the disadvantage is that this will reduce unpredictability, especially if your block size is smaller. So suppose your block size was 4, and you've already assigned 2 individuals to treatment B, then you can guess that the patient 3 and 4 will get treatment A. And then finally, there's stratified randomization. This is where you're going to randomize within certain strata defined by some subject characteristic. Could be age, could be gender, or in a multi-center study, it could be the institution that the patient is in. So on the example here, I've done a blocked, and usually with stratified randomization, you would also need to include blocking. So this is a blocked and stratified randomization. So the strata are male and female patients. Within each block of 4, there's equal numbers of treatments, and then there's going to be equal numbers of male and female patients at the end of the analysis. So again, the advantage here is you're going to balance these potentially prognostic factors, but again, it'll reduce unpredictability. All right, so next is sample size and power. So it's always necessary to consider and calculate the appropriate sample size when designing any study. I've heard a lot of times, oh, this study is really just exploratory, I'm trying to gather information. Well, if exploratory, you're trying to maybe estimate a parameter, well, let's put a confidence interval around that. How many samples do you need to have a certain precision for your parameter estimates? And essentially, it's really unethical to conduct an underpowered study with insufficient sample size to detect a meaningful difference between groups or to have a certain precision in your estimate. So you're going to conduct a study with 5 mice. Well, you're not going to really be able to answer your question, so you're kind of wasting resources and time. And kind of worse is that with a small study, if you're unlucky, you're going to get a false positive result, and this may lead to a series of subsequent studies or experiments based on a false positive. So you really want to know that the result you're getting to make future decisions or design future experiments is solid. You want to know that you're basing this on some rigorous experiment. So I'm going to, again, split up the sample size considerations between descriptive and comparative objectives. And I think here I'm not trying to present a number of different formulas for all different scenarios. I want to give kind of a conceptual explanation of the calculation using one specific example. So in this case, what we're trying to estimate is the proportion of patients with a success. So, and the endpoint here is whether it's success or not for this particular outcome. So what you need to define is your expected proportion of subjects with the success, and then the kind of desired confidence interval width and the confidence level. So generally you would use a 95% confidence level, and then we can determine a certain confidence interval width that would be appropriate. So here I've calculated for different sample sizes for an observed proportion of 60% in your outcome, what the 95% confidence interval would be. So for example, for 5 subjects, your confidence interval would be range from 15% to 95% for this estimate. And basically, it covers the whole range. So it's very imprecise. You don't have very much precision. And as you increase your sample size, you can see that the confidence interval width decreases. So I want to give a kind of concrete example. This is a study I'm working on at Dana-Farber, where they're trying to look at the feasibility of a communication intervention targeting the early treatment period in pediatric oncology. And the primary endpoint here is the feasibility of this intervention. And they defined it as whether the patient's family completed a conversation with the primary care team during this early treatment period. So when talking to the investigator, we expected that the proportion of subjects that we're looking at would have success rate of 60% or more. And we wanted a confidence interval width no greater than 35%. So if we did the calculation for the sample size, a sample size of 35 individuals will achieve this desired precision. So for a 60% observed feasibility, the confidence interval is 42% to 76%. Now, there's an alternative approach that we could have used to kind of calculate the sample size. So the idea here is that we can determine the sample size so that the lower confidence limit is greater or equal to a non-promising value. And the non-promising value essentially is the kind of the minimum success rate here that you would accept for you to kind of proceed with the study. So in this case, let's say that our expected proportion is still 60%. But let's say we were unlucky. When we collected the data, the observed proportion was actually lower than this. Well, what is this minimum we're looking for? So let's say that we wanted the success rate to be no smaller than 32%. Then we can calculate the sample size here. So for example, with 10 individuals, the limits are 26%, 88%. So this is too low. With 15 individuals, the lower confidence limit is exactly at 32%. So this is kind of the minimum number that we would need to kind of rule out success rate lower than 32%. Now, of course, if you wanted to have a higher non-promising value, you would need a higher sample size. So let's say you wanted a non-promising value of 45%, then you would need 50 individuals to kind of rule out with 95% confidence that your feasibility rate is not less than 45%. Yes?
So why do you determine one or the other? How how do you make the decision that I'm going to have a non-promising value of 45 or 32, and how do you do the calculation?
So the selection of the non-promising value is really a discussion between the statistician and the investigator. It's kind of like if I asked you for your experiments, if you're going to kind of proceed with a subsequent experiment, what is the minimum success rate you would want to see to kind of proceed? So if in this experiment, in this study, they only saw that this intervention was successful in 10% of the patients, they would not proceed to the next step. They wouldn't do another follow-up study with a larger population. So this is kind of a decision kind of for the investigator to think about, like if I saw a certain success rate, would I go forward with another study or not? And kind of thinking about this, you may want to, and it's also a balance. I mean, you may not be able to recruit 50 individuals for your study, so this non-promising value is too high. So there's a kind of a lot of factors playing into this.
Based on the desired power, right? You do the calculation based on confidence interval.
Right.
But you can also do that.
That's right. So that's the next step I'm going to talk about. So this is just for a simple descriptive objective. So one arm, there's no comparison. But you can also compare it versus a set value to say, I want to make sure that it's statistically more than a certain minimum number. That's the other way to do it. Thank you. All right, so like I said, so the next piece is looking at comparative objectives. So here I need to kind of go into a little bit into statistics. So when we're trying to think about comparative objectives, we need to think about the null and alternative hypotheses. So the null hypothesis is basically the statement that you're trying to test, and the alternative is a statement that you're trying to you're hoping or expecting to be true instead of the null hypothesis. So let's say your objective here is to compare the mean quality of life score between the intervention group and a control group. So your null hypothesis may be that the difference between the quality of life scores is 0 between the two groups. And the alternative is that the difference is not 0. It's greater than or less than 0 between the two groups. So by conducting the test, you're trying to reject the null hypothesis and show that you have evidence that the null hypothesis is not true. So we also need to think about type 1 and type 2 errors. So type 1 errors are basically your false positive, the probability of rejecting the null hypothesis when in fact the null hypothesis is true. So, so in our example, if truly in nature there is no difference in quality of life between the intervention and the control arm, what is our chance for declaring it to be different? What is our error? That would be a false positive. The flip side is a false negative. So this is type 2 error. The probability of not rejecting the null hypothesis when the null hypothesis is false. So in our example, if there is truly a difference between the quality of life scores between the two groups, what is the chance that we will not declare it to be different? And type 2 error is tied to power, which is simply 1 minus the type 2 error rate. So power is simply the probability to detect a true positive. All right, so let's try to calculate the sample size for the difference between two means. So these are some parameters you would want to specify. So you need to think about the type 1 error rate. So typically we pick 5%. You need a p-value less than 0.05. As for power, generally we'd say 80% power is fairly good. You may decide to have a higher or lower power depending on what you're willing to accept. And here I'm assuming that there's equal numbers of subjects in the two, the control and intervention group. You also have to think about the kind of difference in the mean score that is biologically or clinically meaningful. So even though, you can imagine you can have a very large study that detects a difference in the score of maybe 1% or 0.5%. It's statistically significant, but in the clinic, it's kind of meaningless. I mean, that's within the error of conducting the actual survey. So you need to define your difference that you're trying to detect based on some clinically meaningful measure. And then you also need to establish some measure of precision in measuring the outcome. So in this case, we need to specify the standard deviation for the outcome. And for simplicity, I'm going to assume that the standard deviation is equal in both groups. So when we calculate this, so here are some examples. Suppose that, the difference in the mean score is 10 units. And we have different kind of standard deviations, small, 5, 10, and 15. You can see that the total sample size increases. So for small standard deviation, it requires only 12 individuals. But if you have a more variable measure, you're going to need more data, more subjects to really determine, to detect the same difference in the means. In another scenario where we're looking at varying the difference in the means, but fixing the standard deviation, for a very small difference, a small effect size, you're going to need a big sample size to detect the difference. I want to talk a little bit about multiple comparisons. So, we were talking about the type 1 error rates at 5%. This means that if we conducted this study, we would expect a 5% chance that a significant result is a false positive. Now, if we end up testing many outcomes, many hypotheses, we're going to increase our chance to have a false positive result. So let's say, in extreme case, you're testing 100 hypotheses. So even if, in nature, all these hypotheses are not true, so they're all under the null hypothesis, then we're going to see 5 statistically significant results just by chance. These are going to be your false positives. So we want to be careful when we're designing a study and when we're analyzing the study and adjust for multiple comparisons. So a very common approach would be to use the Bonferroni adjustment. And the idea is you're simply dividing the significance level by the number of tests that you're performing. So let's say you're performing 5 statistical tests. So instead of using a p-value threshold of 0.05, you're going to divide this by 5. You're going to make it more stringent. You need a p-value less than 0.01 to be statistically significant. And this has been kind of broadly applied. It's fairly stringent, so it's a very conservative threshold. And there are some alternative methods, which I'm not going to talk about. I just want to highlight there's the Bonferroni-Holm method and the false discovery rate. And I guess finally, when you're thinking about sample size, aside from all those statistical parameters, there's also practical limitations. So how many patients are you going to expect to lose to follow-up or will have missing data, maybe for incompleteness or they don't fill out your survey. So you may need to kind of expand the number of subjects you accrue so that after deleting these missing data, you're going to have the appropriate sample size to address your study objectives. Sample size may be limited also by the availability of subjects, the very slow accrual rate, and also your study budget. So to me, sample size calculation is more of an art than a science. You really have to talk to the investigator, figure out the limitations, and kind of find the right balance between having enough subjects and running the study in like a practical, time-efficient manner. So the last piece is writing the analytic plan. We want to make sure we define the statistical methods for each objective before we start the study. And it's also important to define the analytic cohort for each objective, which subsets of the subjects will be analyzed. I mean, it may be clear, maybe all the subjects for all your objectives, but if you're looking at subgroup analyses, which subgroups are you going to be analyzing. It's also important to define any stopping rules that may end the study early. So for example, you may decide to stop the study if you see that a certain intervention is much more successful than the control intervention, for example. And you also want to specify any planned interim analyses. So if you're going to stop in the middle of your data collection and do kind of interim analyses, this may lead to an inflated type 1 error rate, and you would have to adjust for multiple comparisons accordingly. So just some examples of writing the analytic plan. So one objective to compare the mean quality of life score. So the analytic plan will be the two-sided students' t-tests will be used to compare the mean quality of life score between the intervention and control groups. And for our feasibility outcome or objective, we can say that the proportion and 95% confidence interval of patients for which the intervention was administered will be calculated. So in summary, careful study design is critical to the success of biomedical research studies. Investigators need to think about defining the study objectives, the outcomes, the study population, selecting an appropriate experimental design, calculating the sample size and power, and then defining the analytic plan. Thanks very much. Happy to take any questions at this time. Great. Great. Yeah, thanks.
Yeah. Yes, it will be available online, yes. Okay, thank you for Clement to give a very nice, descriptions for the study designs, especially how to get the measurements at each endpoints and how to define those variables, and for the sample size consideration and the power calculation. Okay, so I will pick up from here and to talk about the details of some statistic analysis here. Okay, so yeah. So actually, Clement has finished all this, how to, formulate the research question and the hypothesis test and data collection. And then I will talk more about the distribution of the variables, and then the statistical method will be used. And for this talk, actually, we'll only emphasize on some introductory statistic methods, such as t-test. I think Clement also mentioned that t-test and the non-parametric version of the t-test, like a Mann-Whitney test, and Wilcoxon test, and here chi-square, and the one-way ANOVA, and the simple linear regression, and so on, and also to use the SPSS and the SAS. I will try to use both, and here we do not have SPSS and the SAS installed, but I will give you some SAS program and the SPSS pictures to show how we can use SPSS and the SAS to conduct those statistical analysis. And okay, so as we mentioned, like Clement mentioned, all these statistical methods are dependent on the variables. Okay, it's really dependent on independent variables and the dependent variables. Okay, now if there is only one population, okay, like one group of the data, and then it's dependent on the outcome variable, like the dependent variable. If the dependent variable is continuous, we can certainly use just one simple t-test to compare the average value. Okay. Now, if the outcome variable is a categorical, just like like categorical variable like success and fail, and then we can use chi-square test, chi-square goodness fit test to test how the differences between the observed and the expected counts by using chi-square test statistics. This is the simple case with only one population, one group. Okay. Now, suppose there are two group comparison. If there are two populations, and if the outcome variable is a continuous variable, so we'll use the independent simple t-test. Okay. So but if the sample size is smaller, and if it doesn't follow the normal distribution, we may have to use the non-parametric test, like a Mann-Whitney U-test or the Wilcoxon test. If the data, but if the sample size is large enough, okay, and then as you know by the central limit theorem, right, the average value is always converged to the normal distribution, so we're not that worry about the distributions. Yeah, okay. And now suppose for the for the independent variable is two matched group, okay, two population, actually it's one population but two matched group. They are related just like pre and post. So there is dependencies, okay, between those two groups. So in that case, we cannot use the independent simple t-test. Instead, we have to use a paired t-test. Okay, pair the t-test for the continuous variable, and for the categorical variable, we can use the repeated logistic regressions. Okay, and for the continuous variable, yes, we can also use the the mixed model, like mixed models for that. And pair the t-test, just a special case of the mixed model with only 2 time points. If we have more time points, and we can certainly apply by using the mixed models. Okay. Now, if we have more than 2 groups, like 3 groups comparison, and we may have to go to the one-way ANOVA, and we're going to do that today. We'll cover this today. And okay, now if we have more than 1 independent variables. Okay, so in that case, we need to consider some models. If the outcome variable is a continuous or ordinal model, we use the linear regression or Poisson regression if it's ordinal, counts data. And if the outcome variable is binary, okay, like yes or no, so in that case, and we have many of the independent variables, and we use logistic model as we mentioned, or we may use the repeated logistic model as well. Okay, so again, all these statistical methods are all depend on the distribution of the data, the distribution, the type of the data. Okay. Yeah.
Do all those assume equal variance?
We're going to talk about that. Yes, that's a very good question. Okay, so yeah, all the with equal variance, we have certain tests. Without if the assumption of the equivariant failed, and then we use different approach for that. Yeah, we'll talk about that. Yeah, good question. Yes. Okay. So again, and we just follow, Clement mentioned that before we, begin with the descriptive statistics, to, give some report as what's the, mean, standard deviation, and the confidence interval. And for the continuous data, And for the categorical variable, we do whatever counts a percentage, try to give those descriptions for that. And then we move to the bivariate analysis. I usually always suggest researcher, to do the bivariate analysis first, okay? If those two variables, if not then related, there's no need to put into the final model usually, okay? So I always suggest, people, will do the, bivariate analysis first to find out the significances, okay? If there are many variables, and then, we do some bivariate analysis. If both are continuous variable, we run the correlation. If one continue, and then with group variable, we do the t-test and one way ANOVA, and so on. And then as the last stage, we're going to run some statistical model. And here I just talk about the linear model, linear regression model, and then we'll talk about the more advanced statistical model, such as structural equation model. Yeah, for the next. Okay. Now, I will begin with a very simple example here, and we talk about, the randomized control experiment design for the two groups here, okay? So the idea here is try to compare the new methods, okay, for, what make the improvement of the math grades here, okay? So just like we, those subjects are randomly assigned into two groups. One is the treatment group, or new method, or new drug, sometimes called new drug, and then, the control group is placebo group, okay? So, and just, ordinal training group here. Now, after they trained, okay, with these, methods, okay, and the treatment versus control, and then we record the values, okay? Here is the math grades, okay? So, and okay, so this table shows, oh, sorry. So this table shows, just present those simple data with two groups here, treatment versus control groups, okay? Yeah. So here is the t-test. We use the t-test to compare the significant difference between, the average values in terms of the two groups. Now, as you mentioned that there are two different types of the t-test here. One is the equivariant assumed t-test, okay? So we follow, we use this, yes, formula, and the equivariant not assumed, and we use this formula with two different types of degree of freedom. And we also need to test that by using the Levine test, okay? If we run the SPSS or SAS, and it will run the Levine test for the equality of the variance first, and then we can make choice, to see which t-test we're going to report. Yeah. Okay. So here is the, okay. Yeah. Yes. Okay. So for even to run the t-test here, we also still need to check some normalities I mentioned, and to check the, to see if the data is normal distributed, and then we will do the normality test first for the smaller sample size. Like for this example of the data sets, the sample size is less than 30, so we may need to, check the normal distribution first. Yeah. So here is the data in SPSS. And I'm going to, to talk a little bit about how to use SPSS. The good feature of the SPSS is like that, okay? We can import the data, for the categorical data in a numerical format here. It's the numerical variable here. And we can also define the value neighbors, okay? So in that case, which means we can install all this information in SPSS, yeah, and then generate a nice output with those value neighbors, okay? So in SPSS, if we go to the variable view window, we should be able to define all these, value neighbors, so-called value neighbors, okay? So here I present the data in a numerical format and also in the, value neighbor format here. Okay, so in SPSS, and we can run the independent sample t-test, okay? So yes, in SPSS, there is an analyze menu here. Whenever you click analyze menu, all the statistical procedures are all listed, okay? Now, compared to other programs, and compared to SAS or R, for SPSS, we do not need to remember all the syntax, okay? And you can just go to the, GUI, just use GUIs and go to the drop-down menu to click on Analyze, Compare Means, and then, check the, independent sample t-test. And then just follow, the steps, and then put the dependent variable as the test variable, and to define the grouping variable, one for the treatment, the other for the control, and then you can run the t-test here. Okay, now here is the output. So you can see that the first table gives the discrete statistic for both groups, okay, for two groups respectively, and from this output, you see that there is average value differences, okay? But in statistics, we like to know those differences are significant at 5% confidence, at 5% error or not, okay? So we always compare the p-value with 5% significant level here, okay? Now, and again, which t-test we're going to use there? There are two different types of the t-tests here. Actually, those two values, two t-test statistic values are very close. Usually, those two values are very close, okay? So we use the Levine test to test the equality of the variance, okay? Now, for this example, since this p-value is greater than 5%, so the non-hypothesis of the equivariate is not rejected. So in that case, we can use the first t-test, which is equivariate assumed. We use the first t-test, and here is the test statistic, and the 28 degree of the freedom with the smaller p-value, so the non-hypothesis is rejected. The non-hypothesis is rejected, which means there is significant difference between those two groups, okay? Again, and we mentioned that we may want to check the, the distribution of the outcome variable. Thanks, Clement. I know you have another talk. No. Okay. Yeah. So here we also mentioned that we can also use SAS to run the program, okay, to run the independent sample t-test in compared to SPSS. And in the SAS here, first of all, we need to import the data. In SAS, usually we do not have the data in spreadsheet, but we can import the data into SAS system here by using this plot import command. And then we can check the, the assumption of the normal distribution by using plot univariate here, okay? And then we select the QQ plot for the outcome variable of the math by the group. So basically, we're going to check the, the normality distribution for two individual groups here, two independent groups, okay? So here is the output by using the QQ plot. Okay, now those two QQ plots look like close to straight line, okay? Which is closer to the normal distribution. However, the test statistic, for one group is rejected. You can see that those p-values are more than 5% for one group, but not for the other group, okay? So in that case, due to the, smaller sample size, which may, it is worth to check, to use the non-parametric test to check it, okay? So we run the t-test first, and then compare the results with a non-parametric Wilcoxon rank test, also called the Manwini-U test here. But we run the t-test first, okay? So in SAS, the command of the t-test is plot t-test here, and then the variable here is the testing variable, is the outcome variable, and the class, and we put a categorical variable group here for the t-test, okay? Again, in the SAS, the output also give us the, test of the equivariant here, and which is not reject, okay? The equality of the variance is not reject, and then we can use the pooled t-test here, and those are the same t-statistical value you have saw in the SPSS, and then we do the analysis of the t-test of the equal means is reject. The analysis of the testing of the equal means is reject. So the conclusion is, okay, the mass grade of the two methods are significant difference. Okay, so the new method has, will make the mass grade much higher compared to the, ordinal method at the 5%, error significant level here. Yeah, okay. Now, since, as we saw before, one group failed the normality test. So it is worth to check with a non-parametric test. Okay, the non-parametric test sometimes it's called the Mann-Whitney-U test. Sometimes it's called the Wilcoxon test. Actually, those two tests have the exactly same numerical test statistics, so they are equivalent. Okay, so in SAS, yeah, we have we use the plot non-parametric command, one-way command here, and we have the test variable. Test variable is the outcome variable, grouping variable here. Okay. Now for the non-parametric measure here, okay, we have we do not need assumption for the distribution, but we still need the assumption for those observations. They are, independently, identically distributed, so-called IID distributed, and then the shape of the spread of the distribution are the same. So which means those two populations, two groups came from the same distribution, even the underlying assumption of the distribution is not that important, but we still assume those two populations have the same distribution shape here. And then we can run can use the non-parametric test here. Okay. So the non-parametric test is calculated based on the rank, but not the actual values. Okay. So basically, in calculation, for the non-parametric approach there, they rank the data from rank 1 to the highest rank, and then do some calculation based on all these ranks there. Okay, so, and in the non-parametric test there, they also calculate asymptotical, t-test and the z-test statistic, okay? For this example, both z and the t-test has very small p-values, and then the null is rejected. But the more important is here we have the exact test of the Mann-Whitney-U test here. This is exact test based on certain mathematical calculation. We'll be able to get the distribution of the exact test and to calculate the observed p-value here, which is also less than 5%. So the null is rejected. Okay. Now suppose we have more than two groups here. Yeah. Okay. So we cannot use the t-test, right? If we have the 3 and more groups, and we may need to consider the one-way ANOVA just to compare means, but for more than two groups like 3 and more. Okay, so we're going to use one-way ANOVA, this so-called one-way ANOVA. So, and I will give an example based on a real data, a sample of a real data, which is the current population survey of 2009. I make a random sample of the 100 observations out of the huge population, and then input the data into SPSS and SAS to do some statistic test. So again, the null hypothesis here is assume that all the 4 geographic regions have the same average incomes, okay, have the same average personal total income. Yeah, so there are two variables. Actually, one is personal total income, the other is the family income. So we're going to test the personal total income. Okay, so my null hypothesis here is assume, okay, there are 4 geographic regions, and assume they all have the same personal total income. And then the alternative hypothesis is no, they are not the same, okay, which means they may have 1 or 2 pairs have significant difference in terms of the average value of the personal total income here. Okay, so here is the data in SPSS spreadsheet. I will show SPSS procedures first, and then to show the SAS program. Okay, in SPSS, it's also under the Analyze menu. We click on Analyze, Compare Means, and then one-way ANOVA. And then you put the test variable as the dependent variable, which is PTOTINC, stands for personal total income. And then the factor variable is the grouping variable. Here is the region, okay, with 4 regions. Okay, and then I click on the, I clicked on the option menu and try to get the descriptive statistics. And for the 4 groups. Okay, so here is the SPSS output. It shows the average value, standard deviations, and the confidence intervals for all these 4 geographic regions, 4 groups, and then with the F-test, with the one-way ANOVA test here. Okay. Now, for this example here, the F-test statistic is small and p-value is large compared to the 5%. So the null hypothesis is not reject. It's not reject. Okay. So the null hypothesis is not reject. So in that case, we conclude that there's no significant difference among the 4 groups. Okay. Among the 4 groups. Okay. Now here, there is no robust test of the equality of the means. Okay. This is a asymptotical F distribution, and which means if the equivariant is not assumed, so we use this robust test of the equal of the means here. Okay, and in SAS program, I'm going to show how would you to test the equal means equivariance by using SAS program here. Okay. Now this can be displayed by using the arrow bar of the with the confidence interval of the 4 groups here, and in SPSS we go to the graphics menu and click on the graphics, next see dialog, arrow bars, and then you follow this. Just follow the picture. Actually, you do not need to remember all this procedure, but you can just just by nature just follow those procedures, arrow bar, and then click define, click a simple arrow bar, and then define, click define, and then dependent variable and the grouping variable, and then you can just run those those arrow bars. Okay, so this is the confidence interval for those 4 groups. Okay, since there is overlap of those 4 confidence intervals, right? So it shows there's no significant difference among those 4 groups in terms of the average of the personal total incomes. Okay, and now the next picture shows that the arrow bars with significant difference. Okay, here I still compare the personal total income but over 3 age groups. Okay, so I make the young group here, middle age and older age here. Okay, so you can see that those group 2 and the group 3 have significant higher personal total incomes compared to this younger group. Okay, but there's no significant differences between those 2 groups. Okay, but there's no overlap of the confidence interval with group 1 to group 2 and 3, but there's overlap with group 2 and 3 here, with the middle age group and the old age group here. Okay, we can run the SPSS, and then we can check the multiple comparison there, and it shows that there is significant difference between pairs, and no significant difference between those 2 pairs here. Okay. Yeah. Now the next, I'm going to show how can we run the SAS program for the one-way ANOVA. Okay. And for the SAS, yes, we always need to use the program to do. Yeah. Okay. So we use the GLM, general linear model. GLM stands for general linear model, and data equal to test. Suppose I have input the data here, and the class, and then followed by the grouping variable. Here is region, and the model is the SAS command, and then dependent variable personal total income equal to region, and which is independent variable. Okay, if you run the regression, you use the same. You can use plot regression. You can also use the plot GLM as well. Okay, now since we're going to run the one-way ANOVA, we like to do the multiple comparison here. So we added the options command of the means and the region. We like to display the discrete statistics for the 4 groups, and then to do the multiple comparisons by using the two-key method here. So this option of the two-key method to do the multiple comparisons. Okay. Now actually, okay, if we get the non-significance, and for the F-test here, okay, because there's no significant difference of the among 3 groups, and in terms of the personal total income by using the F-test statistic, there's no significant difference. There's no need to do multiple comparison. Okay, Yes, so yeah, if there's no significant difference, so there's no need to do multiple comparison. Instead, here, if I run this, grouping variable as the age, you will see there is significant difference. Okay, so in that case, it was to run the multiple comparison here. Okay. Yeah. Okay. Now, and this slide shows the test of the homogeneity of the variant for the one-way ANOVA for the 4 groups here, and the hypothesis is not reject. Okay, it's not reject. So we can still use the just the normal observation, and then use the homogeneity assumptions, and one-way ANOVA use the F test. Okay, use the F test here. Okay. Yeah. Okay. Now we also similar to the t-test here for one-way ANOVA. They are all based on the distributions of the normality of the dependent variable, the distribution of the dependent variable. We all assume that the dependent variable follow the normal distribution, especially for smaller sample size. Okay. Now, since this is a survey data, the sample size for this example is quite large. It's 1,000. Okay. So we always get good power. The sample size is large. If it's significant difference, we always have the power over the 80%. But it's worth to check. It's still worth to check the distribution. Okay. As you know, usually the income data do not follow the normal distribution, because the personal total income, the income data usually is truncated to the left-hand side. There are many of the lower values and then some of the outliers on the right-hand side in terms of the histogram of the normal distribution. So usually those data fail the normality test here. Okay. So this is a SAS program again to check the the normality the normal distribution here, and then this p-value is all smaller than 5%. So the normal distribution has been rejected. So we would like to try to use the non-parametric version of the one-way ANOVA. Okay, so the non-parametric version of the one-way ANOVA, this is also Wilcoxon test here, and then the test variable still personal total income, and the class variable is region. So we use the non-parametric test, which is plot non-parametrics one way, and then test variable is the personal total income, and the class variable is of the region. So we run that, and I think we have the same results there. Yeah, Cruz-Wallis test shows that the p-value is also greater than 5%. The hypothesis of the equal, it's not equal mean now, it's equal median, it's non-reject. Okay, if we run the non-parametric test, we're not going to test the equality of the average value of the mean, but the equal median here. So it's non-reject. Okay. Now this slide shows, okay, those box plots shows the median plot by using a non-parametric test, shows median plot here, and you can see that there's not much differences among those 4 groups. Okay, there's not much differences among those 4 groups. Yeah. Okay. Now the next model we're going to talk about is the simple linear regression. Okay, talk about a simple linear regression here. Yeah. So there are 2 variables. Both are continual variables. Okay, both are continual variables. Okay, for example, and then the outcome variable here we use is also the average of the personal total income by year, and then the x variable here is years of education. Okay, so I aggregate and the preview the spreadsheet data and by the years of education to make the average value of the personal total income by years education, and then to apply the linear regression model. The region is like that. As I mentioned, the income data usually does not follow the normal distribution, but if I aggregate the data by years of education, okay, I calculate the average values per years of education. So based on central limit theorem, the average value converge to the normal distribution, okay? So in that case, we can get very nice of the, model fit for the linear regression here. So you will see the R square is above 90% here, okay? So the linear regression, the equation is a line equation here, okay? Yeah. So we try to analyze how impact of years education on the personal total income here, and then we can calculate the predicted value based on the estimate of the beta coefficients, based on estimate of the beta coefficients to calculate the predicted value here. Yeah, okay. So for the linear regression, I will present the SAS program here. Yeah. Okay. So we can use PROA GLM, and we can also use PROA regression. REG is PROA regression here, and data equal to edu. I import the educational data here, and I use the title command and the model, which is the personal total income equal to the years of education, and I'm going to plot the the personal total income versus years education, and to do the residual plot here. Okay, so again here I will also need to check the residuals. Okay, the assumption of the linear model is that the residual has to be normal distributed and has to be independent with the predictors, with the independent variables. So I will use scatter plot of the residual versus the independent variable to check if the residual is random distributed. I will also run the QQ plot, the straight line plot, to check if the residual is normal distributed. Okay. Yeah. So this is the output. Okay, based on the regression. This is output based on regression. So you will see that the R square, okay, is about 94%. Okay, 94% of the R square. So it's very high here, and the estimate of the beta coefficients here is also significant with very small p-value here. Okay, so in the PROA regression, I save the output value here. In SAS, I create an output data file, so-called a myout here, and to store the residual value, and to further to check the the normality plot of the residuals. So for the PROA univariate, so the data at this time is equal to the output data set from the regression procedures here, and we're going to check the if the residual is normal distributed or not. Okay, so I use the QQ plot to check that. Yeah, I use the QQ plot, and then to find out that it's close to a straight line. Usually I would say it's okay. According to this QQ plot, we say yes, this residual is close to the straight line, and which means it follows a normal distribution. Okay, the residual does follow the normal distribution. Okay, now how do we interpret the results? Okay, from the linear regression here. So yeah, we have to estimate both intercept and the slope. So I plug in the intercept and the slope to make the predict regression equation here. Yeah, predict the value. So yes, so I use the estimate, intercept, and the slope, and to write out a predicted equation here. So for example, because here this is negative value, okay, some people may argue, okay, why you get the negative intercept? Why? Yeah, it's because, okay, and what's the intercept here is the value when the years education equal to 0, right? Yeah, so that's why. And sometimes people like, to make a center of the independent variable, okay? If I make a center of the independent variable, I use this, years of education minus the average value, and then this intercept will be a positive value, which is the estimated value when the, years education is the average value, okay? So they will make more sense, yeah. So that's why here I will try to calculate those predicted value. For example, if the years education is equal to 12, yeah, so I plug in to this, predicted equation to do the calculation. Okay, this is equal sign. Why become the minus sign here? So we predict the personal total income is about 35,000. Okay, so it's positive value. Okay, yeah. So if this x equal to 0, then you get the negative value. But usually this never happen of years education equal to 0. So yeah. Okay, so the R squared is the 94% again, which means years of education explained almost like 94 of the variations of the personal total income. So this is a very strong relationship. Okay, if I just do the, if I use the subject data, okay, do those scatter plot, I will not get that strong relationship. Okay, but for this example, I use the aggregate data by the years of education, so get a very strong relationship. You can see from this, regression plot here. In a SAS and in a plot regression command, I made an option there to ask for a regression plot here. So we have the fitted regression line, yeah, across those scatter plot, those pairs here, and it also shows R squared. Yeah, which is 94%, and then those predicted regression equation is here. Okay, so this is a regression plot, a linear regression plot here. Yeah. Okay. Now next, I'm going to move to the chi-square test. Okay, before and up to now, all the outcome variables are all continuous, right? All the outcome variable, personal income, and then the math score, they are all continuous variable. So we use the independent sample t-test, one-way ANOVA, and the linear regression. Okay. So the next topics, okay, we're going to study. It will be the chi-square test. So here, actually, you can consider one is outcome variable, the other is and the independent variable, or you could just say to check the relationship between two, categorical variable here. So chi-square test, actually, it is a non-parametric test. Okay, it's used to test the association between two categorical variables, to test the association between the two independent variables. Okay, so the non-hypothesis here is slightly different from before. Okay, and for the previous, statistical procedure, like a t-test, one-way ANOVA, usually we say, okay, the average value is equal, or if the estimate of coefficient is equal to 0. Okay, but for the chi-square test, the non-hypothesis is, there is no association between two variables. Okay, so that's the non-hypothesis of the chi-square test, which means those two variables, column variable and the row variable, are independent. The alternative thesis is there is association between two variables. There is association between two variables. Okay, so the chi-square test statistic is calculated based on the assumption of the independencies. Okay, under the non-hypothesis of the independencies of the column and the row variable. Okay, we can calculate the expected value. We can calculate the expected value is the row total times column total divided by sample size here, yeah, and then we sum all these differences, okay, between the observed value and the expected value. We sum all the differences between observed and the expected value, and to get the chi-square test statistic. Okay, yeah. And according to this formula, you can see that chi-square test statistic formula. Okay, so if the observed value is quite different from the expected value, which means if my expectation is wrong, okay, so these differences will be bigger, right? So in that case, chi-square test statistic value will be larger, and then the p-value will be smaller. Yes, okay. So the non-hypothesis will be rejected. Okay, will be rejected here. Okay. So in SPSS, okay, to do the chi-square test, okay, again, we go to the Analyze menu, yeah, go into descriptive, and then, to ask for cross-tabulation to create a two-way table first, okay, to create a two-way table first. And then we can also click on the statistical menu and the push button to ask for the chi-square test statistic. Now, in the cross tab here, there is a push button of the cells here, and we like to also to have the expected value and the no percentage. And then we can click on the statistic if you run the SPSS to ask for the chi-square test here. Okay. So here is the output. Okay, we have two variables here. We try to test if there is any association between gender and the personal total income. Okay, at this time, the personal total income is a categorical variable into three categories: lower, medium, and high income. Okay, so it's a categorical variable with only three values. And then we try to test if any association between gender and then the personal total income, and also we can try to test in terms of percentage. Okay, in terms of percentage, and the analysis can be said that there is equal probabilities of the higher income for both male and the female, and the alternative thesis is the proportion are not the same here. Okay, now if we check this two-way table, we see that for the female subject there, for the female subjects, there is 7.6% of the observations in the category of the higher income compared to male. There is about 19% of observations in the category of the higher income. Okay. Now for the lower income here, and for the female, it's about 54% in the category of the lower income, but compared to the 40% of the male in the category of the lower income. Okay, so you can see those percentages are quite different. Okay, so by guessing, I would say yes, there could be some association between between gender and the personal income. Okay, so I run the chi-square test statistic. and which is in the next slides. Okay, it shows there is significance. Okay, there is significance of the chi-square test statistic here. Yes, okay, so I do the calculation. Actually, SPSS can do all this calculation. SPSS or SAS can do all this calculation, and we get the chi-square test statistic is about 34, and then with the 2 degrees of the freedom, and then this is reject, which means there is association between gender and the personal income Yeah. Okay, and yeah. Yes, so that is in SPSS. That's SPSS output here. Yeah, and in SAS, I just quick to show the SAS program, and for the chi-square test, which is in the plot frequency command and the table, which is 2 categorical variable, gender, sex, and income. Here, the income is in 3 categories, and we ask to get the expected counts and the chi-square test statistic. So that's the SAS output, which is quite similar to the SPSS output here. Yeah, just in different format, but same numbers here. Okay, I think I used all my time here, so still have 1 minute left. If you have any questions, do you have any question? If not, we save the question to the end. Okay, thank you. Okay, so our next presentation will be Dan, and he will give us the presentation for the structure equation model. Thank you.
Slides on here already, or?
No, I don't think so.
Oh, okay.
Did you have your flash?
I don't have a flash. Can I pull up my email?
Okay, yeah. Oh, okay. So I
Or
did not
have my
save it.
laptop, if I can find my laptop.
You want to?
I have flasher there.
You can use my flash drive if you want. Or you don't. You can connect to your.
Sorry about this. Do I just hold this?
You throw it in your pocket, whatever's easier.
Okay, put this over to the side. Thank you. Okay, I'm going to get started so that. All right, it stopped showing now. I don't know which to use here. Screen went blank for a second. All right, thank you. I'm going to get started so that we have some time for questions at the end. But I'll introduce myself first. My name is Dan Gunderson. I'm the methodologist at the Survey and Data Management Core at the Dana-Farber Cancer Institute. And what I do there is I help investigators who use our services to design survey studies, whether it's a data collection protocol or developing self-reported instruments, what we call in the medical field patient-reported outcomes instruments. And that can be as simple as just writing a few survey questions and testing them to make sure they can get good information, to doing more advanced psychometric modeling, which you'll see an example of today. And so I'm going to talk about structural equation modeling, which is a very broad framework to do statistical analysis. And what I'm going to talk about is some key concepts and terms. I'm going to talk about how do you identify a model and how do you estimate the model. I'm going to show you some examples of how to do this in R, which is a statistical programming language, and specifically using what's called a Lavand package, or the Lavand package, which is a structural equation modeling package written for R. And then I'm going to show you an example of some very popular types of analysis that you can do in the structural equation modeling framework. And I have some learning objectives here. They're not really strict learning objectives. These are just things I hope you sort of take away at the end of today, because we only have about 45 minutes. And structural equation modeling is a very advanced, very broad topic, and so we can't cover everything and have real learning objectives. But I want to make you familiar with what structural equation modeling is, what the language is, if you were to do it, how do you do it in statistical software, which requires you to know the language of structural equation modeling. And so we're going to talk about how do you, what kinds of data and what kinds of research questions lend themselves to doing analysis in the SEM framework. We're going to write the model in equation form and in graphical form, so we're not going to do math. That's not what we're going to do today, but if you are going to do it, some software is going to require you to identify the model and write the model out using equations. And some software, you can actually draw the model using figures, and it'll estimate the model for you. So you need to be familiar with both of those, depending on which software you choose to use. And then we're going to talk a bit about interpreting and assessing model fit and stuff like that. And I'm really going to emphasize the things that are a bit unique to SEM models. But some of the things that she talked about testing for normality, those are things you'll have to do as well. But I'm not going to talk about it because she just talked about it. And there's some additional things that are more unique to SEM modeling. So the first thing is, what is structural equation modeling, or SEM modeling? Structural equation modeling isn't really a model. It's a framework. It's a very general framework for fitting statistical models or for doing statistical analyses. And I put often complex in parentheses there because it lends itself, by the end of the lecture, I hope you can sort of appreciate that this framework lends itself to answering fairly complicated research questions fitted within a single model. And there's a lot of familiar models that are special cases of structural equation modeling. For example, you can fit a linear regression, a simple linear regression, in the SEM framework. Most people don't do it because it's so easy to implement in just regular software, but you can do it. It's a special case of an SEM. You can also do a factor analysis in SEM. That's one of the more confirmatory factor analysis is one of the more popular types of SEM models that you can do. And I call them measurement models in today's lecture because that's a more general term for it. And that's what I spend most of my time doing, is assessing latent constructs. So I do a lot of factor analysis type stuff, and so I do a particular type of structural equation modeling. And one of the great things about doing analysis in the SEM framework is that most of the software is very flexible in allowing you to put constraints on which parameters to estimate and which not to estimate, or if you want two variables to have the same regression coefficient or something like that, it's fairly easy to implement. So it's very flexible in that sense. And so some common analysis that you can that are popular to do in the SEM framework. The first bullet is just to show you how general of a framework this is. And so some descriptions of SEM is it's a framework where you can relate one or more dependent variables to one or more independent variables. And you can't get more general than that when you're talking about statistical modeling. But that's a broad set of models you can do there, right? You can do a multivariate analysis where you have many independent variables, or one or more independent variables, or you can do a multivariable analysis where you have one dependent variable and one or more than one independent variables. But two types of models that are sort of very popular to do in the SEM framework, which if people have these types of research questions, they'll tend to do an SEM analysis, is to confirm a hypothesized causal mechanism, which often can be more complex than just A causes B, like smoking causes cancer. It can be A causes B through the path of C and D or something like that. And I'll have some examples to show you later on so that becomes less abstract for you. And the second one is confirming a latent variable measurement model, or if you have hypothesized that a set of variables that you've measured are manifestations of a theoretical construct or a construct that you can't directly observe, you can do a confirmatory factor analysis. And this SEM provides a framework for you to really test your model. Oops, wrong way. Okay, so there's some key concepts and some key terms that are commonly used, and I want to define them for you so they're not foreign to you the first time you read them. So we really have two types of models in the structural equation modeling framework. The first is a measurement model. That's what I just talked about, which can be a confirmatory factor analysis. That's when you're trying to estimate a latent construct or a theoretical construct that you can't directly observe from a set of variables that you can observe, that you believe are manifestations of that variable. And I have an example of that later too, so that's less abstract. And the second is the structural model, which really relates all the constructs of interest for you together. So like if you have one theoretical construct, say depression causes smoking or is related to smoking, for example, then those are the two, that's the structural model. A causes B, or A is related to B. Mediation is the effect of an independent variable on a dependent variable operating through an intermediate variable. So A causes B through some third variable C, for example. And I have an example of that, so you don't have to listen to me talk about letters. And moderation is really a statistical interaction. It's when an effect of an independent variable is different on a dependent variable is different depending on the level of some other variable. So if the relationship between depression and poor health behaviors were different for men and women, then gender would be a moderator for that association. So this is a graphical presentation or a graphical written model for a measurement model. And I'm going to take a second. This is actually from a real study, although I simplified it so that it would display better on the slide. And that text doesn't do so well here. But I just want to point out what the different components of this graph is so that you're able to read it and draw it if you have to, if you were to do your own analysis. On top there, you see a circle or an oval. Sometimes it's oval shaped. Whenever you see a circle or an oval shape, that's typically the latent variable, the theoretical construct that you're interested in measuring. You see a number of, you see these squares at the bottom here. Whenever you see a square, that's typically a manifest variable, or what's sometimes called an indicator variable. Those are variables you actually can measure and that you took measurements on from your sample. So in this case, we're trying to measure, and you can't see the text up there because it's too small, and I apologize for that. We're trying to measure somebody's knowledge level of multi-gene panel testing for the risk of cancer. And you can't directly observe somebody's knowledge level of something, so that's a latent construct. It's a theoretical variable that we're trying to estimate. But we can create a bunch of questions, kind of like a quiz you take in class, that are manifest variables. And here I just labeled them. There's a question on inheritance, like can you inherit cancer? Treatment impact, if you know that you're at risk for cancer, does that impact your treatment? Yes or no. Discrimination, if you know that you're at risk for cancer because of a gene mutation, can that be used to discriminate against you? And then risk reduction, are there things you can do to reduce your risk of cancer? And depending on how somebody answered to those four knowledge questions that we're actually able to measure, we use that to estimate the latent variable. You can see unidirectional arrows from the latent construct, the circle, to the squares, the manifest variables. Whenever you see an arrow going from one variable to the other, and the direction of the arrow means one causes the other. So in this case, somebody's knowledge of multi-gene panel testing causes their responses to our actual questions. If somebody has very low knowledge, that causes them to get a lot of them wrong. If somebody has very high knowledge, that causes them to get a lot of these right. These little arrows that point, the sort of curve in on themselves, they go from one variable to the same variable. That indicates the variable's variance. When you fit a model, that would be residual variance. And this variable or this arrow right here that's bidirectional, that goes between treatment impact and risk reduction, that just means that they covary. There's a correlation between those two variables, but we don't make any causal assumptions there. We're just estimating covariance or estimating a correlation or some association between those two variables, but we don't know which causes what. And in this case, since you see that there's arrows pointing to them, it will be a residual covariance, which we'll talk about more later. Yes, please.
So when you say latent variable, do you mean like the dependent variable, like independent and dependent?
That's a great question. I was going to talk about that on the next slide, but we'll talk about it here too because it's important to be able to identify that here. So in this case, a latent variable is your independent variable, which can be confusing in a measurement model because you're using your dependent variable to infer somebody's level on the independent variables, which is reverse of what you're used to thinking about, right? And that's why measurement models can tend to be a little bit foreign to people and a bit complex to read about and talk about. But once you get into it, it becomes more intuitive. And I think towards the end of the class, when we have more complicated models, you'll see how it all fits together. So in this case, the independent variable is somebody's not knowledge level, and the dependent variables in the measurement models are these 4 knowledge questions that we measured from them. So this is general mathematical notation for a measurement model like the one you just saw. I have a more concrete example on the next slides. But what I want you to appreciate here, or what I want you to sort of get from this, is one, it's a very familiar equation. So if you just look at the first one, it looks exactly like a multiple linear regression, right? Except we use different notation. We use different symbols to indicate the different things. So in this case, I used y to indicate the manifest variable. So here in the equation form, you clearly see that that's the dependent variable, right? V here is an intercept. Lambda is like a regression coefficient, but often that's what we call a factor loading. But that would be analogous to the beta in a multiple regression. The eta, the little n-looking symbol, will be the latent construct, which is actually what we're estimating in a measurement model. And then the dot, dot, dot just means you can have more than one latent construct determining what you observe in the manifest variables. The second thing I want you to notice here is that we have multiple equations. And so here we have one up to j variables that we're measuring. And that could be 2, that could be 10. In this study, it was 25 variables. So we have 25 dependent variables. We have 25 equations. And so really what I want you to get out of here is that we don't have one equation. It's more complicated than even a multiple linear regression, because we have a system of equations that we want to estimate simultaneously. And I used y and v and theta, but depending on what software you use and what textbook you read, they can use different notations. Some people use x, which I don't like to use because x is most commonly associated with an independent variable, and here there's dependent variables, but people will use it, so you just have to be familiar with what it is. So in the example that I just had on the figure, we have 4 equations. So somebody's response to the question, the knowledge question about inheritance, is a function of the intercept and their knowledge level of genetic testing. And there's a regression coefficient there, or a factor loading, depending on how you scale the variables. And you have the same for treatment impact, for discrimination, for this risk reduction. And all these variables are a function of a single latent variable. In a more complicated multivariable model or measurement model, you could have different manifest variables being a function of one or more, either the same or different latent variables, and that's what's called a multidimensional variable. So when you have to write this in a software to specify to the software what it is you want to estimate, they don't make you write 25 equations, because that would be really, really long. And so to try to have some consistency in their syntax, they'll actually write latent and some symbol, some operator that tells the software what kind of analysis you want to do is a function of all these manifest variables that we've collected data on. So this is a more familiar framework in that we're estimating the latent variable, and that's a function of all these manifest variables. When in reality, it's actually the reverse we're actually doing. And depending on the software, the operator will look differently. So M+, for example, actually doesn't use a symbol, it uses words. So for factor analysis, you will write knowledge is by these variables, because it's a function of or it's manifested by these variables. And you'll see some different ones later. So for the previous examples where I had the 4 variables, you would just see genetic testing knowledge, some operator, which depending on the software, inheritance, treatment impact, discrimination, and risk reduction. Much simpler way to write it, and it makes it more consistent with all the other types of analysis you can do in the SEM framework. Any questions on that so far? See, we're not going to do math. We're just going to look at some equations. Okay. So something that's a bit unique when you have a measurement model, or any model that includes a latent variable that you want to analyze in the SEM framework, is that there is no natural unit of measurement. So if you're measuring depression, you might have 30 questions, like the Beck depression inventory, that are Likert style questions or something like that, that might go from strongly disagree to strongly agree, or whatever labels they have for each of the data points. And there's some numeric value to each of those response options. But those are really arbitrary and are just there to facilitate quantitative analysis. So you might create a sum score that ranges from 1 to 30 or 1 to 100 or whatever the case might be. But that's just as arbitrary as saying we're going to have from 10 to 600 or 10 to 1,000 or whatever the case may be. And so we have to tell the software somehow that this is an arbitrary unit of measurement. And the way that we do that is the software tends to do that automatically, but you need to know what the default behavior is in case you want to change it, because depending on how you identify the model, this is what's called identifying the model, or this is a necessary constraint to identify the model. It will affect how you interpret the output. So most software that I'm familiar with, the default is to fix the first path coefficient, so the first regression coefficient, for example, to be constrained to 1. And then all the other regression coefficient will be relative to that first coefficient. An alternative to that is to fix the variance of the latent variable to be 1. So we tell the software, whatever estimate comes out at the other end, I want the variance of the latent variable to be 1. Then you've standardized the latent variables. Typically, that would be 1 with a mean of 0, although you can sometimes tell it to have a different mean. And that puts it on the z-scale or the standardized scale. You do have to make some choices in how you're going to estimate the model. I'm only going to talk about these two here because they're the most popular ones, but there's a whole bunch of other types of estimators you can use. The first is maximum likelihood, which if you do generalized linear modeling is typically used. I'm not going to go through the details of what each of these are, but some of them have limitations. And maximum likelihood assumes that you have conditional multivariate normality, which means that all the variables together, actually the residuals of all the variables together after you fit the model, have a multivariate normal distributions. And you can use some of the techniques that Jie talked about to assess that. And there are multivariate analogous multivariate tests you can do. Or you can just look at the univariate distributions, some bivariate distributions. And if you find, which is most often the case in the types of data that I work with, that normality is violated, that normality assumption is violated, there's some things, more advanced statistical methods you can use to adjust for that so that you do get unbiased variance estimates, for example. And there's, depending on the software, the default might be to provide you what's called Satora-Bentler adjustments, adjust the chi-square value for the model, or you can get what's called robust or sandwich estimators of the standard errors. It just makes an adjustment for the amount of non-normality so that you do get unbiased statistical tests. The other one, other estimator I'm going to talk about is what's called the asymptotic distribution free. That name is mostly associated with continuous variables. For categorical variables, it's usually called weighted least squares. Weighted least squares is very similar to an ordinary least squares regression, but it doesn't seek to minimize the difference between the predicted value and the observed value for each individual data point. It seeks to minimize the difference between the observed value and the predicted value for each pair of correlation. So across the entire correlation matrix or covariance matrix, it tries to minimize the deviation in there. But the weighted part, the weighted part here is that it implements a weighting algorithm to adjust for the degree of non-normality in your data, which can be pretty complicated. But one of the limitations of weighted least squares is that it's very computationally demanding if you have a large model with lots and lots of variables because it has to inverse the variance of the covariance matrix, which tends to be very large. And so as an alternative, there's a few alternatives that have been developed, and one of the popular ones is what's called diagonally, which I misspelled, unfortunately, I apologize, weighted least squares, which is the same concept, but it uses a smaller weighting matrix. So it requires less computational power if you have very complicated models. And I'm not going to talk too much about, so which is the appropriate one to use depends on a lot of factors. And there's been a lot of simulation studies out there, or there's been a good amount of simulation studies out there that you can access to make your decision. But the simulation studies have shown that diagonally weighted least squares tends to work pretty well in that it produces unbiased point and variance estimates. If you have relatively small samples, I've heard numbers like 200, which often is large samples depending on what area of research you're in, and not too complicated of a model. Weighted least squares with some various adjustments for the degree of non-normality works well in large samples, but does not work well in smaller samples. And maximum likelihood, if you have normality, works pretty good in large samples. And relatively large samples you can get, and I'm using very general terms here because it depends on how complicated your model is. The number of samples you need to be able to, what constitutes large and small. It tends to produce unbiased point estimates, but the variance estimates can be affected. So just like you do for a linear regression or any type of regression, like a logistic regression, you want to assess how well your model fits the data. Because if you have a model that doesn't fit your data very well, then what does that tell you about the population if it doesn't even fit the data? And there's a lot of what's called global fit indexes or fit statistics that you can use in structural equation modeling. I'm going to talk about the 4 most popular ones, but there's a whole bunch out there if you just Google it. In fact, if you Google David Kenny and SEM, he's a quantitative psychologist at the University of Connecticut. He has a great web page that actually discusses the various ones, what the limitations are, which ones are no longer in use for various reasons. I'm partial to it because I was a student of his when I was at UConn, so. But it is a really good website. So the first one here, and I'm not going to talk about the details here, I just want you to get the concept of what these various ones are measuring, is what's called the chi-square model goodness of fit. It compares the model that you estimate against what's called a saturated model, or sometimes a just identified models. A saturated model is when every possible parameter that you could estimate or estimated by the data is most of the time, at least if you're in a measurement model, it's not a very useful model, but it's the best fitting model you can fit to your data, and it wouldn't generalize very well most of the time. But the concept here is that if the model that you fit is not statistically different from a saturated model or a best, in quotation mark, model, then then you have a good fitting model. So the null hypothesis here is that your model and the saturated model are equal, and so you want to fail to reject that. So you want a p-value greater than 0.05 or whatever your threshold is. And if you have that, you can conclude, yes, I have a good fitting model. The limitation here is that it is very strongly influenced by your sample size. And in a lot of SEM analyses, you have complicated types of modeling, and you have very large sample sizes. So almost always that will be rejected. And so that, the result of that, if that was the end all and be all of model assessment, then a lot of model, we wouldn't learn a whole lot. Yes, please.
Very sensitive to the sample size. It's also sensitive to the number of the parameters to estimate.
Oh yeah, absolutely. So
right?
it's also, so if you have a, yes. So if you have a very complicated model and there's not a huge difference between the saturated model and your model, then there's not a big difference in terms of the degrees of freedom between those two models, and it's easier to fail to project it. If you have a very simple model, then more often that statistical test will be rejected because there's a huge difference there.
More unknown variant covariance term.
Yeah.
It's more, it's less likely to be rejected.
Yeah, so there's not a penalty for the complexity of your model here. And that's what some of these other models, model fit statistics address. So the Tucker-Lewis index and the comparative fit index, they're very similar to each other. They both make an adjustment for the complexity of the model. So they actually take the chi-square value and either divide by the number of degrees of freedom or subtract the number of degrees of freedom. So they have an adjustment built into it for how complex your model is relative to the model you're comparing it to. But for these fit statistics, you're not comparing it to a saturated model. You're comparing it to a baseline model or a null model, which is analogous to an R-squared, where you're comparing the model that you fit. And so that if you're doing a linear regression, you're comparing your final model against an intercept-only model. This is similar to that. It's not exactly that, but you're really constraining all the possible paths to be 0. So you're telling the software to estimate a model where the value of all the coefficients are going to be 0. So it's like an intercept-only model. And then you're comparing it to that. And it ranges from 0 to 1. In this case, you want to be as close to 1 as possible. And some of the common cutoffs are 0.9 to say you have an adequately fitting model, or 0.95 to say you have a good fitting model. In some instances, it might make sense to say that to use a higher cutoff than that or a lower cutoff to that. If all the research that's been done in your area so far have gotten, say, a comparative fit index of 0.97, 0.96, and you end up exactly at 0.9, then your model is not as good, whatever that means, as these other models. It's not as good fitting as these other models. On the other side, if all the research that's been done today, if you're trying to develop a new latent measure, for example, have had CFIs of, say, 0.85, 0.88, and they've been pretty close to 0.9, and you end up with 0.93, then that's something that you could be excited about. So I would discourage, cutoffs are great as a general guide, but they only really make sense when you interpret them relative to what's common in your field. The last two look more directly at so the standardized root mean squared residual is a standardized difference between the observed and what's called the model implied correlations or covariances. Model implied here is predicted. So you fit your model, and then you predict what the covariance would be based on, or covariance matrix or correlation matrix would be based on that models. And then you calculate a standardized difference between all the pairs of correlations in the observed and model implied. And in this case, you want to be closer to 0. And if you end up exactly at 0, that means you have no residual covariance, no residual correlation. And the common cutoff value is 0.08, but the same disclaimer that I had for the previous measures apply here, in that you really have to benchmark it against what's common in your field of research. And the last one is actually probably one of the more popular ones. It's the root mean square error of approximation. And the reason that this is a very popular one is because you can do a statistical test on it or against some cutoff value. And it really compares your data against some hypothesis, alternative hypothesis. And so it tends to track the root mean square residual fairly well, but it's not exactly the same, at least in the data that I work in. And 0 indicates perfect fit. You want to be closer to 0. Some of the common cutoff values are 0.06, 0.08. Some people use 0.10. That's less commonly used, I've seen. But you can calculate you can do a statistical test. So if you have 0.7 and large samples, or moderate large samples, you can test whether it's statistically different from 0.8. And if it isn't, you can say, okay, it's close enough, or it's not statistically distinguishable based on some error level that you set. Or if you reject it, you can say, okay, I don't have a good fitting model and we need to collect more data or something like that. I would never encourage anyone to rely just on sort of the global model fit measures, because you want to inspect. You can have a good fitting model based on these summary measures, but still have important residual correlations that are meaningful in your area of research that you want to interpret or maybe want to address in some way. So you want to inspect the residual covariance or correlation matrix, which again is just the observed correlation matrix minus the model implied or predicted correlation matrix. And if you have large residual covariances or correlations among some item pair or a number of item pairs, then that suggests that the model doesn't reproduce what you observe in the data for those two variables very well. So you'd want to look at the actual residual correlation matrix, but there are some statistical tests you can do, and I have examples of this later. You can look at what's called the modification indexes or indices. That's a score test, or if you're familiar with econometrics, that's the Lagrange multiplier tests. Or you can fit a bunch of nested models where you allow a parameter to be estimated or restricted to not be estimated or to be 0, and you compare them using the likelihood ratio chi-square statistic. And if they're not significant, then it suggests that you don't have significant residual covariance. And if they are significant, it suggests that you have significant residual covariance. And you might want to address it in some way. So I'm going to switch back to some examples using R, but first I want to talk a bit about what R is and sort of how it works. So R is an open source statistical programming software, as opposed to like SAS and SPSS and Stata that are more statistical analysis software, although at this point in time the difference is getting more blurred. But it was developed for people that try to develop new statistical methods. And it was historically mostly used by people who do that type of research. Although now, and as part of its base package, or if you just load or install R on your laptop or desktop and you open it, it does have a lot of statistical functions in there. You can do linear regression, you can do principal component analysis, you can do factor analysis, you can do generalized linear modeling, you can do a whole bunch of different types of modeling. But it also has a lot of user-written packages for specialized kind of analysis that you can install, or if you're a good programmer and have a lot of theoretical statistical knowledge, you can write your own packages. And the Lavaan package is one of those packages that's user-written. It's written by a researcher, a psychometrician called Yves Roussel, who's at Ghent University in Belgium, and it's becoming a very, very popular SEM package for R. And what you see in sort of the shaded area is the syntax you write. And I'm going to show you an example of a path model and how you would conduct that analysis using the Lavaan package in R. And on top here, you can see that I'm just I'm making up some data. I'm just making up the correlation matrix that we're going to analyze, because I want to emphasize a couple of things in the outputs. I want to control what ends up on the other side so I can make some comparisons. So say we have a study where we're hypothesizing that the effect of education on healthcare consumption, the amount of healthcare you use, like you go to the doctor or you buy cold medicines, you buy supplements, is mediated by income. So here you have a mediation analysis. So education leads to higher income, and higher income in part leads to the amount of healthcare you can buy. It's various type of analysis an economist might do, for example. And so we have three variables here. We have education, income, and healthcare consumption. And at the bottom here, I've generated the correlation matrix, where you can see that education and income has a correlation of 0.4, education and healthcare consumption has a correlation of 0.5, and then income and healthcare consumption have a correlation of 0.6. So they're all fairly highly correlated with each other. So we expect to see some significant or some substantively large results. So Lavaan is one of those packages of softwares that makes you write the model out in equation form. And when I do that, I try to label my syntax or my code so that other people can read it, so that it's more reproducible. So the first thing I do is I type library Lavon. That just loads the package into R. It tells R, hey, I'm going to use this package now. You only have to do that once. You don't have to use that anytime you fit a model. And then I specify what my model is. So I have a direct effect here that I hypothesize that education influences healthcare consumption in some way. So I first specify that equation, and you can see the little, you can see the little tilde symbol. In Lavon, the little tilde symbol, the squiggly symbol, means regressed on. So what I'm doing here is I'm specifying a regression. And this C multiplied by education, in this case, I have to label the coefficient that I want to estimate, because later I'm going to generate a user-specified estimate, so I don't have to do it manually outside of the software. And then I have the mediation equation. So I have income regressed on education. So far we have two equations, healthcare consumption on education. And then the mediator was an intermediate income, intermediate outcome. Income is regressed on education. And then we have the mediation regression, which is healthcare consumption on income. And I'm interested to see the degree to which income mediates that effect. And the way the statistic for that is multiplying the two mediating coefficients. And so I'm just telling the software, like the colon and equal means there's a user-specified a statistic I want you to show me, so I don't have to calculate it myself. And then the total effect is just the effect of education on healthcare consumption, irrespective of any mediating relationship. So now I've specified the model. I've assigned that to an object that I called model because it's the model. And now I want to actually estimate the model. So I'm using a function called SEM for structural equation modeling. I specify what the model is. So the first argument to the function is SEM. In this case, I'm analyzing the correlation matrix directly. So I'm telling the software to access the correlation matrix. So they say sample.cov. It doesn't distinguish between correlation and covariance. So you can use the COV stands for covariance. You can use that argument for correlation matrices. So the number of observations here is 551. I made that up. And I'm telling it to use the maximum likelihood estimator. So I'm assuming a normal distribution or that it's not affected by, which probably is not the case. So there's two things I want you to see here. The first thing is, well, there's a few things that I want you to see here. On top here, you see minimum function test statistics. That's the chi-square statistic. That's 0 in this case. So what we have is a saturated model. In this case, it's a path model. We don't have any latent variables. That's OK. That's OK to have in this case. If you had any latent variables in this model, you'd not want to see that. And down here is the output, which is basically like a regression output. In this case, since the input that I had the software access was a correlation matrix, these are standardized regression coefficients. So the relationship between healthcare consumption and education after controlling for income is 0.31. The regression of income on education is 0.4. I'm sorry, income on education is 0.4. Healthcare consumption on income is 0.476. These are in standard deviation units. And here you have the variances. And here are the defined parameters. These are the ones that I defined. I just told the software, I want to see these. I want you to calculate it for me because I don't want to have to do it myself. And so AB is the indirect effect, is 0.19. So, and the total effect is 0.5. So if you remember from the correlation matrix, the correlation between education and healthcare consumption was 0.5 in the correlation matrix. So we reproduced that. That's the total effect that we estimated. But the indirect effect is 0.19. So of that total effect, there seems to be, and the z-value is 8, and the p-value is well below 0.05. So it would be, so these are significant results. And this is what that relationship looks like in a path diagram. So if we were to diagram the, if we were to draw this out with the regression coefficients as labels, you can see that education has a variance of 1 because this is a standardized scale. All of them have been standardized to be have a mean 0 and variance 1. The direct effect is 0.31 as a partial direct effect here. Remember the regression between education and income was 0.4, so you see all these labels. And here you see the unidirectional arrows. So education causally impacts healthcare consumption, education causally impacts somebody's income, and income causally impacts healthcare consumption. But this is a more complicated causal relationship called mediation analysis. And the variance, the residual variance of healthcare consumption is 0.56. So about 44% of the variance in healthcare consumption is explained by this model. And for income is 0.84. So 2 ways to see the model. Okay, now we're going to switch to a factor analysis or a confirmatory factor analysis or a measurement model as I'm calling it here. And this is a real study, and I'm going to show you some more diagnostics here. So again, I'm telling R to load the Lavin package, and I'm writing out the model. So the hypothesis here is that we have a unidimensional knowledge construct for multi-panel gene testing, and that somebody's level of knowledge in this area determines the responses we see to the quiz we gave them. And so the model is written fairly simply. I'm just calling the latent variable gen testing knowledge. And then you see the equal sign with the tilde. You can read that's the operator for a latent variable. You can read that as genetic testing of knowledge is manifested by, and then these variables. There's actually 25 variables in the data set. To make it more display better for the slides, I just picked a few of them. And then I fit the model. In this case, I'm calling the CFA function, which stands for confirmatory factor analysis. And I'm assigning all the results to an object called CFA fit. So the first argument in the CFA function is knowledge model. So I'm just telling you, this is the model I want you to estimate, which I wrote above there. In this case, I'm having it read the raw data directly as opposed to me inputting a correlation matrix. So say data equal no micro.df. That's the data frame or the data set that I want to analyze. And in this case, because these are binary variables, correct, incorrect responses, I'm using the weighted least square with a mean and variance adjustment to estimator, which is a weighted least square with robust standard errors, essentially. And so I'm adjusting for the fact that these are non-normal data. So we actually get a lot of output here because there's a lot of things that's going on. Oops. So here I want you to see that now we have some model fit statistics to read as part of the output. And the default behavior of this package is to just give you the chi-square, a model chi-square. So you can see the model chi-square. It gives you the diagonally weighted least square. That's not the estimator that I used. I used weighted least square with mean and variance adjustment, which is under the robust column. And so we have a chi-square value of 49 with 20 degrees of freedom. And that gives me a p-value of 0.00. Where you see the scaling correction factor and shift parameters, the statistics you can use to compare to other software that might scale it differently, but will produce equivalent p-values, at least in large samples. And down here we have the sort of model output, the parameters that we estimated. And so the first thing I want you to see here is that the coefficient for the first question, which is just labeled knowledge 1 or no one factor, is fixed at 1. So the default behavior here was just to fix it at 1. And so now I have to interpret all the other variables relative to that. And so we're not going to spend a lot of time interpreting it, but so the intercepts are all 0 here because we have categorical variables, so they're not that much interest. except for the actual latent factor, which is also fixed at 0. The thresholds, if you're familiar with logistic regression, or in this case, this would be analogous to a probit regression. These are thresholds that would, let's see. And so down here, you can see a scaling factor, which is 1 here. That tells you that the correlation matrix that they estimated was based on what's called the tetrachoric correlation coefficient, or the polychoric correlation matrix. That's very similar to fitting a generalized linear model with a probit link. So it assumes a latent scale with a mean 0 and a variance of 1. If you had a logistic link, it would be 1.7 something, I believe, or pi squared divided by 3. So in my case, I don't want to really look at the raw. I don't want to fix the first coefficient to be 1, because that makes it harder to interpret for me. I want to look at the actual correlations between the latent construct, somebody's knowledge level, and each of these manifest variables. So I use this standardized solutions function and just tell them I want the standardized solutions for this model, and then it gives me the output for that. And most of this will be, or a lot of this will be repetitive. Some of it will change slightly. But the top there, you can see that genetics testing knowledge, and you have the same operator that we used when we wrote the model out. And on the right-hand side, we have the manifest variables. And EST.std stands for estimated in standardized units, or estimate in standardized units. And these are just correlation coefficients, right? And so the correlation between the between the latent knowledge construct and the first knowledge quiz question was 0.46. So those two are very strongly correlated. The correlation between the second, for the second variable, is only 0.04 with a p-value or a z-value of 0.6. That's not as significant. That suggests that that variable does not tap into this construct. And so we might want to modify the model. Here that model is written up as a diagram. And you can see this is the same type of measurement model that I drew when I was talking about this is how you draw a latent variable model. You can see the latent construct has unidirectional arrows. The correlations are labeled for each of the arrows, so you can read the correlations for each of the variables. And you can see the residual correlations, residual covariances here, which is called uniqueness in factor analysis. SEM pass is just a function in R that you can use to generate these types of plots, so you don't have to sort of draw it yourself. But we want to go a step further and want to see, okay, we had at least one variable that wasn't correlated with it. Do we have a good fitting model or don't we? And so I'm using the fit measures function, and I'm assigning all the values to a object called fit_ms, or fit for measurements. And I'm only going to pull out 2 of them because there's about 20 in there that you could actually read, and I just want to be selective in which I interpret. So the comparative fit index is 0.92, so it's above the 0.9 threshold, which is at least adequate based on conventional criteria. But the root mean squared error of approximation is 0.05, which is pretty low. It's at least below 0.6, it's below 0.8, it's below 0.1. But I'm also asking for the root mean square error of approximation for the null model, where all of the coefficient would be constrained to be 0, because David Kenny, who I mentioned before, he's done some research on sort of how good are these various measures, and he's found that when the CFI is relatively high for the null model, it's not that informative for the model that you actually fit. And he uses a cutoff of, I think, 0.158 or something like that. And in our case, for this model, the null model is, the REMSA for the null model is 0.168. And so we won't put too much interpretation into the CFI in here, because we know that likely is underestimated relative to what's a good fitting model. So we have what looks like a good fitting model based on this global fit statistic or model level fit statistic. But I want to go one step further and see, do we have item pairs that aren't, the correlations for which aren't reproduced very well by the model? And so I've created this plot here that's kind of color coded. And the bluer, the darker something is blue, the stronger the positive correlation. But I have the numbers in there too. And the darker something is red, the stronger a negative correlation between two variables. The color coding is just to be able to easily see stronger correlations, so you don't, because sometimes if you have 25 variables, that becomes a very large matrix, and reading each of them individually and trying to keep track of it becomes harder. So the color coding just helps with interpretation. And you can see that variable, the 20th question we had on there, and question number 2 has a fairly strong residual correlation, right? And so that suggests that the model doesn't reproduce, doesn't fit that pair very well. And there's some other ones that are fairly large that may or may not be important. They may or may not be interpretable. So the next step is to do some statistical test for that residual correlation. Is this just a nuisance, or is it just random, or is this something that we need to address somehow? So I'm using modification indices, and I'm using the modification indices function in R to inspect them. And in this case, I'm just showing you the first 5. And I'm comparing the critical value for MI scaled, because we used a robust estimator, against the critical value for a chi-square distribution with chi-square value with 1 degree of freedom, because the modification index is approximately follows an approximate chi-square distribution under the null hypothesis, if that was true. So I set alpha at 0.05, and after adjusting for multiple comparisons, the critical value rounds to 8.28. And so in this case, I have one variable pair, which is variable number 2 and variable number 20 before that has a critical value above that. So that's a significant residual correlation, which suggests that we don't have a really great fitting model for at least for those 2 variables, possibly for more. So we have some options of how to address this. Some of these options are, you can either free the residual to be estimated by the model. So we rewrite the model and say we want an estimate for how the strength of these 2 correlations, and then we go through this process again and see if we have a good fitting model. And for those 2 variables, presumably we would, but we'd have to check all the other variables as well. We could eliminate one of those 2 models, and there are some different ways you can decide which to eliminate. That depends on what your goals are. Or if it is, or if both of these variables are absolutely crucial for your model, you can just leave it and say, okay, the model is not perfect, but these 2 variables are really important, so we're going to interpret them with some caution. That would presume that you don't expect them to be correlated. Or you can leave it as if, do some comparison modeling where you you might allow it to be estimated by the data, even if theory suggests that it shouldn't be, or you might eliminate it and compare those results for whatever you want, for whatever type of inference you want to make against the model that you initially fit. And if they're not substantively different, you would disclose that type of comparison modeling that you did and say, based on our comparison modeling, we didn't arrive at different conclusions, and so we're going to go with what theory suggests and present that model. So you have lots of different options, and there could be more options than this. Okay, so lastly, which is probably what I think is the strength of doing analysis in an SEM framework, is the ability to combine a measurement model, essentially combining a factor model with a path model, or a factor model with a more traditional regression model. And so say you have a study that hypothesizes that the college-educated people have greater knowledge on average for multi-gene panel testing than those without college degree. And Clement would be upset with me because I was not specific enough in my hypothesis here. And so I write out the model. The first part of the model is the measurement model, which you saw before. That hasn't changed. And then I have the structural model. So I labeled the structural model, which is just genetic testing regressed on college, which I operationalized as somebody having college degree, a bachelor's degree or higher, versus somebody having less than a bachelor's degree. This is not a real research question that the investigators are interested in. It's just something I'm doing for illustrative purposes today. And then I'm using the SEM function like I did before. I'm specifying what object is the model. I'm reading the data, the raw data set directly. And in this case, since we have a measurement model that is contained of categorical or binary variable, and the structural model has a continuous latent construct, but a dichotomous dependent variable, I'm using the weighted least square with an adjustment for non-normality. And this is the output we get. And again, the default behavior is to fix the first coefficient of the measurement model to 1. In this case, I'm not interested in interpreting it because I've done a separate analysis to validate that model, or it presumes that I've done that separate analysis. And so I'm going to scroll down to the regression heading, where you can see that genetic testing knowledge is regressed on college. And we actually see a negative correlation, which is curious. So we'd want to check our data, check our model, make sure we coded everything correctly, because this is counter to what we hypothesized. So this suggests that those with a college education scores 0.318 lower on average than those with without a college education. And the p-value is 0.000, so at the conventional 0.05 threshold, this is a significant finding, even if it's counterintuitive. And this is what that model looks like if you were to draw it out. So now you can see the measurement model has been rotated. You don't have to rotate it. I just like to read it that way. And it's to the right, where you have all the residual covariances. You have the correlations between the manifest variables and the latent knowledge variable that you estimated, which you've already validated. So you kind of know what that looks like. And over here, you have the regression output between college and knowledge, which is -0.3, and with a residual variance of 0.91 for, let me go back one step, for somebody's knowledge level. So do you have any questions about what I asked? I went a bit over my time, but I can stick around for questions. If you don't have any, I added a bunch of resources that you might want to look into. If you're interested in using R, that's the web pages. RStudio is a very helpful IDE, an integrated development environment, which is kind of like a GUI type system. Oh, it's not a GUI, but it's a software that allows you to access R in a very structured way. There's a web page for the Lavon package. It's one of the, it's published sort of as validation in this article. So if you like to read about statistical software, you can access it. It's pretty dense. If you like measurement models, this textbook is very good. It's by a BU professor, confirmatory factor analysis for applied research. And here's a list of resources for structural equation modeling more generally. LISREL, M+, EQS Stata, SAS, and AMOS are all softwares that you can use, and they all have their strengths and weaknesses. M+ at this point is probably the most popular one. I've used it quite a bit, but it's very expensive, and so I've kind of changed over to R because it's free. But M+ and Stata have very instructive reference manuals where they'll take you through examples in a very sort of non-technical way, which I think is great. And you can access the technical documentation as well. And the website for Lavon has really good examples if you're interested in learning that package. All right, any questions? No questions? Okay. Oh, I guess that's not mine to do. Oh, that's a good question. It should be on YouTube. They'll be on YouTube, right?
Which one?
The presentations?
No, I do that now on the website.
Oh, on the
We were
website.
just live streaming, I believe. I don't know.